So, have you ever actually stopped to think about how artificial intelligence makes its massive, world-changing decisions? I mean, underneath all those sleek, shiny interfaces, AI essentially operates as two things: a meticulous matchmaker and a really diligent prep cook. Today, we're diving into this explainer to unpack some completely fascinating material on data measurements and pre-processing. I am so excited to guide you through this because we're going to uncover the secret mathematical language computers use to literally understand our world. We'll see how they measure things, and honestly, perhaps more importantly, how they scrub our raw, messy reality into something a machine can actually digest.
Here is our agenda for today. Number 1, the math of similarity. And number 2, data preprocessing. Let's get right into it.
Section 1, the math of similarity, or as I like to think of it, the AI matchmaker. How exactly does an AI mathematically decide two totally distinct things are alike?
Okay, to build a solid foundation here, our source shows that before a computer can compare things, it has to level the playing field, right? Imagine trying to compare the weight of a tiny apple to the weight of a massive watermelon. They're on entirely different scales. The machine solves this by standardizing the raw data using something called a z-score. In plain English, a z-score just measures how far any single data point is from the absolute average. If a raw score is below the mean, it gets a negative score. Above the mean, it gets a positive one. It's this brilliant little trick to turn apples and watermelons into one universal mathematical language.
Now, what's really fascinating here is the inverse relationship between how we think of likeness and how a computer calculates it. The data makes a huge distinction between similarity and dissimilarity. When an AI is measuring similarity, the values usually range from 0 to 1. A score closer to 1 means the objects are super alike. But when measuring dissimilarity, which computers often just call distance, it is the exact opposite. Think about it. A distance score of 0 means there is absolutely no space between them. They are completely identical.
And this brilliantly illustrates how computers calculate that physical distance space. The text outlines 3 variations of the Minkowski distance, which, is really just a fancy umbrella term for measuring the gap between data points. First, you have the Euclidean or L2 norm. Just picture a crow flying in a perfectly straight line from point A to point B. Easy. Second is the Manhattan or L1 norm. Imagine a taxi navigating the rigid square blocks of New York City. It can't just drive through buildings, right? It has to measure those right-angle turns. Finally, there's the Supremum or L infinity norm, which simply looks for the single maximum difference between any two traits. It's like comparing two houses and only caring about which one has the absolute largest difference in square footage, totally ignoring the rest of the house.
Let's actually look at how this plays out with medical data using something called the Jaccard coefficient. When comparing patients, say Jack, Mary, and Jim, the AI has to handle what we call asymmetrical binary variables, which sounds incredibly complicated, but it's really not. Think about a fever. If Mary and Jim both have a fever, that is a positive match. That's a big deal. But if Jack and Mary both do not have a fever, well, the computer shouldn't suddenly link them together as having the same sickness just because they share a healthy trait, right? The Jaccard coefficient mathematically ensures that these asymmetrical zeros don't wildly skew the similarity score. So the crucial takeaway here is that a computer encounters vastly different types of information. You absolutely cannot measure hair color the same way you measure someone's rank in high school. For nominal or categorical data, like the color red versus blue, the AI just uses simple matching. Is it a match? Yes or no. For ordinal data, where a specific rank matters, like going from freshman to senior, the computer maps that ranking smoothly onto a scale from 0 to 1. And for real-world data sets that just mix everything together, the AI uses a really complex weighted formula to combine categorical, numerical, and ordinal data into one massive, cohesive distance score.
Which brings us to a super interesting question. We totally get how AI measures simple numbers and categories now, but how exactly does a computer determine if two massive text documents are talking about the exact same thing?
The answer lies in something called cosine similarity. Think of comparing two gigantic library books. The AI obviously doesn't read them like you or I would. Instead, step 1, it represents each document as a bag of terms, literally just a giant virtual pile of the words used. Step 2, it converts these into term frequency vectors, essentially just counting up exactly how many times each specific word appears. And step 3, it calculates the vector dot product. Mathematically, this evaluates how frequently those exact words overlap between the two books, giving us a highly accurate similarity score, totally regardless of how long the actual books are.
Now, that works wonderfully for counting words, but what if the AI isn't just counting words? What if it needs to measure the difference between two complex probability distributions?
How does a machine figure out what gets lost in translation?
Enter the Kullback-Leibler, or KL divergence. Our source data shows that this formula measures the exact gap of lost information. It is exactly like taking a beautifully written book in French and translating it into English. No matter how incredible the translator is, some tiny nuance, some original meaning is inevitably going to be lost in that approximation. The KL divergence mathematically calculates that exact loss. Specifically, it measures the expected number of extra digital bits required to code the samples when the AI tries to use one distribution to approximate the true original data.
All right, Section 2, Data Preprocessing, or the AI Prep Cook. Let's pivot from the AI as a mathematical matchmaker to the AI working in a very, very messy kitchen.
Just like prepping ingredients for a gourmet soup, you can't just throw dirt-covered carrots and unpeeled onions directly into the pot, right? If your raw data is garbage, your AI's predictions are going to be garbage. It's that simple. The research outlines that the AI Prep Cook must first evaluate data across 6 critical quality dimensions. Is the data accurate? Is it complete, or are things missing? Is it actually consistent across different systems? Is it timely? Is it believable, meaning can we actually trust where it came from? And finally, is it interpretable, meaning easily understood by the system itself?
So what happens when an ingredient is just completely missing? Say a customer's occupation is left blank on a web form. There are a few distinct strategies the AI can use here. First, it could just ignore the entry entirely, or the tuple, which is just a nerdy word for a single data record, though obviously that loses data. Second, humans could fill it in manually, but let's be real, that is way too tedious. Third, the AI can insert a global constant, just dropping in the word unknown. Fourth, it can mathematically average it out by applying the attribute mean. Or fifth, and this is by far the smartest method, it can use inference. It leans on Bayesian probability to actually guess the most likely missing value based on every other piece of data it has on that person.
Now, what about noisy data? Imagine a database entry that lists someone's annual salary as -$10. Obviously, that's an impossible error. Here, the machine acts as a digital janitor. It can smooth the data out using binning, which groups data points together and replaces them with their average. It can use regression, which kind of forces those wild data points to fit along a smooth, predictable mathematical line. It can use clustering to group all the normal data together, making the weird outliers visually obvious so they can be tossed out. Or it can use a semi-supervised approach, literally just flagging that -$10 salary for a human being to come inspect. Finally, our AI Prep Cook rarely cooks with just one database. Usually it's dumping multiple massive databases into one single pot. When doing this data integration, the AI has to resolve direct value conflicts. For example, if one database measures weight in metric kilograms and another uses imperial pounds, the AI has to standardize them, or the recipe is ruined. At the same time, it has to strip out redundant, derivable data. If one table tells us a person's monthly income and another tells us their annual revenue, the AI uses correlation analysis to realize it's just repeating what we already know and cleans up the redundancy, so it doesn't double count anything.
Wow, okay, we have covered a lot of ground today. We've seen how machines elegantly measure distance, whether they're acting as a flying crow or a city taxi. And we've seen how fiercely they scrub real-world data in the pre-processing kitchen. But here is the absolute most crucial point to take away from this explainer. AI models are entirely 100% dependent on the mathematical precision of the raw ingredients we feed them, which leaves us with a pretty provocative thought to end on. If a machine's reality is only as clean as the data it processes, how much of our beautifully complex, messy world is being lost in translation just to make the math work? Thank you so much for joining this explainer.